A great welcome to this presentation. So today I will demonstrate analysis of isolated footings under biaxial moments using the ETABS tutorial. So before getting into the details, let me explain some of the background behind the analysis of the footing. We know from our fundamentals that a load set P mx my acting on a foundation can be replaced by an axial load P at position Ex, Ey such that Ex equal to My by P and Ey equal to Mx by P. Now depending on the load position identified through Ex, Ey coordinate, 5 zones designated from A to E are possible, each with a unique distribution of soil stresses. So here is shown a simple sketch to demonstrate these 5 zones. So as you can see that the zones A, these are the corner zones and they are foreign numbers. So for example, this is A, this is also A. And then we have 4 B zones and then there is a center C zone and we have 2 numbers of D zones and 2 numbers of E zone. Now let me explain the characteristics of each zone. For example, let me start with the zone C. As you know, zone C is known as the main core. And the load position for this zone lies within a foundation kern. So we call this area as the kern area. And this is essentially a rhombus with diagonals L by 3 by B by 3. And remember, zone C represents the case of small biaxial eccentricity with the whole of the footing base in compression. That is, when the load position is in zone C, we do not expect any uplifting of the corners of the foundation. Now next is zone A. So as you can see that A is a corner zone and they are foreign numbers. And for this zone, the load position lies in either of the 4 corner rectangular areas. And the size of this area is L by 4 by B by 4. And for a load position in zone A, it will result in large biaxial eccentricity, imposing high triangular compressive stress area. And the design engineers should ensure that a load position in area A is altogether avoided for the design, because a load position in zone A means a very high biaxial eccentricity with the lifting of almost 3 corners. Now coming to zone D, as you can see that these are zone D and they are 2 in numbers, and the load position is such that Ey is much greater than Ex, with the 2 corners of the footing losing contact with the soil, resulting in a trapezoidal compression base area, which means that when you place the load in the zone D, you will have a trapezoidal compression base area beneath the footing with the 2 corners losing contact with the soil. The next one is zone E. It's almost similar to zone D. Only thing is that here the eccentricity Ex is much greater than Ey with a trapezoidal compression base area. So finally we have the zone B. They are again foreign numbers, and this corresponds to moderate biaxial eccentricity producing a pentagonal compressive base area, which means that when the load is positioned in zone B, we'll have a pentagonal compressive base area distribution wherein we have one corner of the footing getting uplifted. And finally, I would like to make a small mention. Here you will find that an ellipse is drawn, and this area we call it as a secondary area, and this secondary area is essentially an elliptical area with a major and minor axis dimensions of 12 by 3 and 2b by 3, and it's always a good practice to maintain the load position within this area. So the designers should ensure that the load position for the set of P, Mx and My as far as possible lies in this secondary area. So remember here I have marked the footing dimensions L and B, and also the particular load position identified through EX and EY is also marked. Okay, fine. So let us start with a problem statement. The response of an isolated footing subjected to an axial load P and biaxial moment Mx and My will be demonstrated here using the ETABS software. So what would be the results to be reviewed? The results essentially include the distribution of soil bearing pressures for various positions of applied load, and finally the results are compared with the theoretical solutions. So the problem data is something like this. The length of the footing L equal to 4 meters and its width is 3 meters, and as will be explained in the ETABS tutorial, the thickness is assumed imaginatively larger number, that is 10 meters. This is to simulate the rigid foundation behavior so that the ETABS results can be directly compared with the standard cases. So the bearing strata that is assumed for this analysis is a medium dense sand strata with a typical modulus of subgrade reaction Ks value of 40,000 kN per meter cube. So for all the 5 zones A to E that we have considered in the analysis, the axial load P is kept constant equal to 1000 kN, and 5 cases of Mx and My values are chosen such that each load position covers all the 5 zones marked from A to E. So as you can see that this is a ETABS model. So I will take right now to the ETABS tutorial to explain the various parameters associated with the 3D model. Okay, fine. So this is the 3D model for the footing that is subjected to the biaxial moments. So first of all, I want to show you some of the parameters that is used for this model development, and these are already discussed in the previous videos. So if you go to the material properties, you'll find that I have defined a property known as CONC. Let me just show you the properties associated with that. So you'll find that the specific weight is set to be equal to 0 because I presume that the footing load takes care of the self-weight of the footing as well. And you will find that the modulus of elasticity E for the concrete is set as 25,000 MPa. Now let me show you some of the section properties that those are defined. The first one is the property associated with the column. Here you will find that I have defined a property known as a COL 500 by 500. Let me just show you the parameters associated with that. So fine. So this column property is used to model the column connecting the footing, and you will find that the material is CONC, and the overall dimensions of the column is 500 by 500. Now next let us see the parameters associated with the definition of the footing. Remember that the footing is modeled using the shell element. So here I will show you the properties, section properties. So we'll go to the slab sections. Here you will find I have modeled a property known as the footing. So let me just show you the parameters. So you'll find that the footing is modeled using the shell thick formulation, and the material property is CONC. And here coming to the thickness, remember I have provided an imaginative very large thickness of 10 meters, and the intent of this is to simulate the behavior of a rigid footing so that the ETABS results can be directly compared with the hand calculations. So otherwise if you are performing the designs, you have to input the actual footing thickness over here. Now I think I have to show you one of the important property that is corresponding to the springs that is used for simulating the soil behavior. Remember that we have defined the so-called area springs in this case. So you'll find that I have defined a property known as ASPR2. I just want to show you the property over here. Remember as our footing will be subjected to partial contact area also, that is with the uplifting of specific corners, we have to model all the area springs using the compression only command. And here as you can see that I have specified the modulus of subgrade reaction K for the associated with the soil as 40,000 kilonewton per meter cube. So these are the main parameters that is used for modeling the footing. And finally, I would like to show you the loads also applied. So here we have selected the nodes. So let me just show you the joint load associated with that. So here you will find that the footing is subjected to an axial load, that is a force in the global direction of 1000 kilonewton, and is also subjected to biaxial moments with mx is equal to 300 kilonewton meter and my is equal to 650 kilonewton meter. And I think that this corresponds to the case B that we have discussed in the presentation. So that's all regarding the important parameter specific to this model, and we are ready to run the analysis. So we'll just proceed to run analysis. It will take a few seconds, and I would like to show you only the distribution of the soil pressures so that you will be able to interpret more clearly the results provided in the presentation. So let me just take the plan view. So it's a base. Okay, I think that this is a deformation, so we'll go for display the soil stresses. So we'll select the soil stress over here. Okay, fine. So as you can see that this is the distribution of the soil pressures below the footing. As so it is very clear, if you just move the cursor around the model, you will find that the pressures. So at this point, you will find that the value indicated over here, it is equal to 0, which means that over this much of area that is marked in blue, that has lost contact with the soil. And you will find that essentially the pressure distribution below the footing is trapezoidal, and this is no actually this for this case it is I think that is 1 2 3 4 5 is a pentagonal soil pressure distribution with the uplifting of one corner. And reviewing these soil pressure values, you will find that the maximum pressure has occurred at this point, and the maximum value is already given over here, that is equal to 219.354. And you can also find the pressure at the other corners. If you just put the cursor over here, you will find that the pressure is 113.4, and here again you will find a smaller value of the soil pressure, that is of the order of say 49.8, and at this corner it is 0. So you can also directly obtain the position of the neutral axis also. Neutral axis, we know that it is the line along which the strains as well as the corresponding soil pressures will be 0. Obviously, it is very clear that if you just move your cursor around these points, you will find that the values at these points are very smaller. That means the neutral axis will be somewhere a line passing through these points. So that's how we have obtained the distribution of the soil pressures, maximum pressure, minimum pressure, and how many of the corners are getting uplifted, and what will be the position of the neutral axis, etc. from the ETABS model. So let us switch over to the presentation now. Okay, fine. So let us start reviewing the ETABS results and also see how these ETABS results are matching with our hand calculations. So the first one, we started with the zone C. Zone C, obviously we know that it is the kern area, and we expect that the foundation base to remain entirely in contact with the soil because this is a small eccentricity case. So you'll find that P is set as 1000 kilonewton, Mx is 150 kilonewton meter, and My is 250 kilonewton meter. So for this set of values, we evaluate the load position as Ex equal to My by P, that's equal to 0.25 meters, and Ey equal to Mx by P, that's 0.15 meters. Obviously, here the load position comes in the zone C. So the soil stress distribution from the ETABS is shown here. And as you can see that I have marked the various corners of this footing as P1, P2, P3, P4. And the soil stresses obtained from ETABS, it is marked in the brackets. For example, here you will find that this corner is having a minimum pressure that is 27.6. This is 89.7. And with this corner corresponds to a maximum pressure of 139 kilonewton per meter square. And the other corner corresponding to 77 kilonewton per meter square. So here from the sketch it is very clear that we do not have any uplifting of the corners. and the entire base area remains fully compressive. Now let us see how these ETABS results match with the hand calculations. So on the right side you can see I made some hand calculations using the CalcPad software, and the values are inputted over here. L equal to 4 meters, B equal to 3 meters, and the values of P, Mx and My are inputted. And we know that this is a case of a small eccentricity, and you must be aware of the simple formulas available to us. So all the corner pressures P1, P2, P3, P4 are hand calculated using this formula, which you must be familiar with. And as you can, for example, the hand calculations provided me P1 equal to 27.08 and the ETABS 27.6. So that's a good matching. P2 89.5, here is 89.7, and P3, that's the maximum pressure, is 139.6 is the hand value, and the ETABS provided me 139 kN per meter square. And finally the P4 value is 77.08, here it is 77. So here we find that for the small eccentricity case there is an absolute one-to-one matching with the hand calculations and the ETABS results. Now let me take you to the other zone. That is, if we have provided the values of P, Mx and My in such a way that the load position lies in zone A. What is a zone A? Obviously we know that zone A, these are the corner rectangular areas. So if we put our load positions in these areas, it will result, we know that, in very large biaxial eccentricity case. So accordingly we set P equal to 1000 kN, that is kept constant, and you can see that the values of Mx and My are set to a very large value. Mx 80,000 kN and My is 1500 kN, and this corresponds to a load position Ex equal to 1.5 meter and Ey equal to 1 meter. So obviously if you mark the values of Ex and Ey, you will find that the load position lies in the corner zone A. So just like the previous case, the soil stress distribution from ETABS is shown here, and the values of the soil pressures at the various corners are indicated over here. As you can see that this kind of the load position results in a highly compressive triangular area. Look here. So you'll find that this produces a triangular highly compressive base stress with the uplifting of three corners. Look here, P1 the soil pressure is 0, P2 it is 0, and P4 again 0. And here we find that the maximum soil pressure is too high, that is 1426. And from the values of the soil pressure, I have also plotted the approximate position on the axis, which corresponds to the zero stress line. So let us see how these results match with the hand calculations. So here the calculations are done again using the CalcPad. We can find that Mx and My, these are the same, 1000 and 1500 kN, with the Ex and Ey as 1.5 and 1 meter matches with this. And we compute here, we have got only one soil pressure, that is the soil pressure at this node, because we know that the soil pressures at the other corners will be 0. So the maximum soil pressure is estimated using the standard formula Qmax is equal to 3P divided by 2 into L minus 2X into B minus 2EY, and this has provided a maximum soil pressure of 1500 kPa. And we find that there is a small deviation from the ETAB results 1426, and this should be due to the accumulation of a very large stress in a particular area of the model. And obviously I am very sure that we'll be able to improve this value of 1426 to take it to near to 1500 if we go ahead with a small meshing size. Currently the mesh size is 0.25. Suppose we take it to say 0.15, we'll be able to take 1426 to a value very near to 1500 kPa. So our observation here is that the load position shown here, it produces a very high compressive stress because the EXEY is such that the load position is in zone A. That is why the design engineers should always ensure that the load position do not belong to the area A. Now let me take you the third one, that's a zone E. Obviously these are the zone E. As you can see that there are two numbers. This is the first area, this is the second area. So here we have again kept P the same, 1000 kN, and Mx and My are adjusted in such a way that we have Ex equal to 1 meters and Ey equal to 0.15 meters to take the load position to the area E. So again, we performed an ETABS analysis for this case. The soil distribution is shown over here. So here you will find that we have the lifting of two corners. Okay, the lifting of two corners, that is the P1 is equal to 0 and P4 equal to 0. And essentially, a load position in zone E, it results in a trapezoidal soil distribution. Here you will find that it is essentially a trapezoidal soil distribution. Just like in the earlier calculation, I have marked all the soil pressures against each corner, wherein you will find that two corners are subjected to the uplift and one corner is having a minimum pressure of say 189.3 and the other is having a maximum of 255.7. Now in order to find out how these ETABS calculations or the results match with the hand calculations, here I have presented a detailed hand calculations made with the calc pad. And here you will find that mx and my, they are 150 and 1000 km and ex and ey 19.15 meters. And the maximum corner pressure is obtained using these expressions. I don't want to read it. These are pretty long expressions. And I would ask you to go through the various journal papers that is reported in literature, for example, in ASCE, Geomechanics Journal, etc., in order to get expressions. Many of the textbooks do not address formula for these zones. So here you will find that the Pmax is obtained as 257.7 and this almost matches very well with the 255.7 obtained from ETABS, and the minimum pressure is 190 which matches with the 189.3. So we find that there is a one-to-one very good level of matching with the ETABS results as well as the hand calculations. So now let me take you to the zone D. So zone D is these two zones, that is a D on the upper side and D on the lower side. Here P is kept the same, that is P is 1000 kilonewton and mx is 750 kilonewton meter and my is 600 kilonewton meter, in order to produce a load position identified through Ex equal to 0.6 meters and Ey equal to 0.75 meters. And again here is shown the ETABS distribution of the soil stresses. As you can see here that two corners getting uplifted. Okay, fine. So it means that this neutral axis position, I think that it has to be shifted a little bit down. That is after the corner 2. So which means that when the load is positioned in zone D, we arrive at a pentagonal soil distribution with two corners lifting off. Now again, a hand calculation is made in order to see how this ETABS results matches with the hand calculations. So from the ETABS we find that the maximum pressure reported is 345.8 and the minimum is 120.8, and we have the maximum and the minimum pressures at the two corners with the uplifting of the two corners results in the zero stress values. And here as you can see that in the hand calculations we have used the same values of mx and my with the ex and ey. It matches with the values assumed in the ETABS results. And the Pmax values and the P minimum values are evaluated using the standard expressions. Remember that these expressions, again, you will not be able to find out in majority of the textbooks. Please refer to journal papers. So here we have Pmax 350.6. It matches 345.6 obtained from the ETABS. And the P minimum is 121.48. That is matches very well with 120.8 obtained from the ETABS. And finally, we are in zone B. Zone B, obviously, these are the four zones, 1, 2, 3, 4 B zones. And we know that this is a case of moderate eccentricity. And for this zone B, we have P equal to 1000 kilonewton and the values mx and my are adjusted in such a way that the load position lies in B. And the mx is chosen as 300 kilonewton meter, my is 650 kilonewton meter, with the load positions identified through Ex equal to 0.65 meters and Ey equal to 0.3 meters. And here you will find that this is a zone. This results in uplifting of one corner, and we have the so-called pentagonal soil distribution. So we have 1, 2, 3, 4, 5 sides. So it's a pentagonal distribution. And for this moderate eccentricity, we find that there is only lifting of only one corner, And here again, the soil stresses obtained from the ETABS, it is indicated in the corners. We find that one corner is having a 0 stress values, and the area marked in the blue, it is a zone of uplifting, and the neutral axis, which corresponds to the line of 0 stresses, is marked over here. And here again, hand calculations are made, and some formulae which are obtained from the journals are used here for the verification. And here I have calculated only the Pmax, and because the formula associated with the P minimum is too long, so I thought I will take only one formula for the Pmax. And here I calculated the maximum soil pressure using the standard formulations 221.4, and this matches very well with the 219.5 kN per meter square obtained from ETABS. Thus, we find that for all the 5 zones, there is a very good correspondence or a good matching level to the order of, say, more than 95% between the ETAB results and the hand calculator values using CalcPad. Thus, we find that ETABS can be efficiently used for obtaining the distribution of stresses, distribution of deformations, also in obtaining the design moments mx and my for the structural design of the footing. So that's all regarding this presentation. If you have any comments, please let me know. As usual, please go ahead and subscribe to the channel. I'm going to present a set of many different kind of tutorial problems so that you will be able to get the real potential of ETABS, because I have seen through many ETABS tutorials that people are essentially using it for the structural analysis, and I want to explore it to its potential in analyzing the foundation problems also. We will consider both the shallow foundations as well as the pile foundations in future. So that's all. Thanks a lot for patient hearing. Have a nice day.